Welcome to the University of Southern California and India Institute of Science second Faculty Research Symposium on COVID-19. Good morning to those of you joining us in LA, and good evening to those of you joining us from India. Wherever you are in the world, we are so glad you are tuning in today as we showcase some cutting-edge research from faculty at both USC and IISc. A special thank you to our symposium coordinators, Raghu Raghavendra and Professor Vijay Kumar. So without further ado, please join me in welcoming to the stage Dean of the USC Viterbi School of Engineering, Yanis Yortsos.
Thank you very much, Stephanie, and welcome to everyone. It is our great pleasure to see everyone here again. About 2 months after we had our first joint presentation and a joint effort in understanding, providing ideas and research in these very unusual times that we live in. I want to welcome my counterpart from India, Professor Yadadin Narahari, who is also a co-sponsor and a presenter of this event as well. And I would like to thank all of you who are participating in this event today, as well as those who are presenting. I wanted to say a few words about what we do at USC right now. I remember the last time we talked, that was about mid-June or like something of that particular time frame. We're all looking forward to the semester to be at least in a hybrid form at USC. Unfortunately, in a sense, the second wave that came in during the summer in the United States terminated those particular plans. And instead of being in that mode and potentially welcoming students to campus, we are going through this semester again through an online-only activity. The campus is open at USC now at 50% for people to restore their research program at about 50%. And so there are people on campus. In fact, I do go to the office every day. I think it's actually probably the safest place in Los Angeles because there are not many people on campus. In my office, I have an office of, I don't know how many square feet with the rest of the offices there. And very rarely you will see someone else. So from that perspective, I think it is great. What is not great is interacting with the students, conducting our business the way we used to conduct it. I teach a class just to understand what are the constraints and the challenges in terms of online teaching. And it's very useful to me because I now have a much better understanding, first of all, of how the interaction happens, and also on the other side, how the students interact with you. And there are many valuable lessons that we learn from this, which I think will be very useful for us as we move on to the next chapter, post-COVID. And right now, the prediction for the university is that we will have a hybrid process and hybrid system in place for the spring semester, which starts on January 15. Our hope is that by then, the epidemic would have subsided significantly, and more importantly, that people will have learned to have a behavior that allows the famous R naught, for which I will discuss a lot in my presentation later on, to become much, less than 1, and if possible, much less than 1, until, of course, there is a vaccine that is effective and being developed. So that is actually how we plan forward. A number of universities in the United States are following similar approaches. That depends on in what place, in what university, in what part of the country. More universities in more urban communities, like in Los Angeles or other places, are much more restrictive compared to, let's say, places that are in isolated communities or in rural areas. I just learned today that the famous football season, in the college football season, will resume at the Big Ten universities, which is in the Midwest. And there is quite a bit of maybe a campaign, if you wish, to restart also the Pac-12 season, which is the universities in the West Coast. So we'll see how this is going to go. In the United States, athletics, have a different way by which they have a different mission, a different purpose, if you like. But this is how is the current situation here at USC. The incidents on campus for COVID are very few. Los Angeles County, the numbers are actually going down significantly. So these are all good indicators. But the country is actually, we want in the country to figure out if there was a recurrence of infections because of the Labor Day weekend, which was about a couple of weeks ago, less than 2 weeks ago. And so that's something that I think people pay attention to. So again, a big pleasure to be here and to co-host this event with our friends at IISc. We feel a lot more special affinity with you because I know that you're also going through a period of time that we've gone through before. And the good news is that there is a recovery from the other side, and hopefully we'll together in a global way get around this contagion and be able to resume a life as usual, or at least in a post-COVID world. So thank you, and I'd like now to give it back to Tiffany.
Thank you so much, Dean Yortsos. Thank you for those updates, and we look forward to your presentation later on today. And that was big news about football. I didn't hear that yet. So thanks for delivering that interesting news. All right. Now I'd like to welcome to the program the chair of the IISc Division of Electrical, Electronics, and Computer Sciences, Dr. Yadati Narahari.
Thank you, Tiffany. Good morning, Yanis. Good morning, Raghu. And good morning to all the participants from USC. Good evening to Vijay, and good evening to all the participants from IISc. Exactly 2 months back, we had a wonderful event where many of the lively projects ongoing at the USC and IISc were showcased. We had an excellent event. COVID-19 has affected all our lives like never before. I don't think we have seen anything like COVID-19 in our lives. It has affected all walks of life in the world. And it has also given an excellent opportunity for us to find a new normal. And at the Indian Institute of Science, first of all, I would like to convey the greetings of our director, Professor Govindan Rangarajan, to all of you. At the Indian Institute of Science, in the last 6 months, I think the Institute has responded in a marvelous way to the pandemic. We had an ongoing semester during March, which was completed by extending the semester by 2 months. And our new semester, which was scheduled to commence on August 1st, is now postponed to October 1st. And all the 900 to 1,000 students who have been offered admission to the Institute will be joining the Institute virtually on October 1st. And they will be coming to the campus physically only by February 2021. So during these past few months, the division of EECS, many faculty members and grad students have spent their time on some really exciting projects. We have almost like 15 exciting projects being carried out in the division of EECS at the Institute, and some of those projects are going to be showcased today. I must thank Raghu and Vijay for pulling this event together. And I think the momentum that we gained 2 months back by organizing the event will be kept going through this event. And I'm hoping that we'll have a really memorable and a very lively and exciting collaborative partnership between USC and IISc. So with my greetings to all of you again from the Indian Institute of Science, and looking forward to a great set of talks today. Thank you very much. And I would like to give it back to Tiffany. Thank you.
Thank you so much, Dr. Natahari. It's amazing how productive IISc still is during all this time. So thank you so much for those updates. And now for what we've all been waiting for, we are going to begin the technical sessions of the program. I'd like to welcome Vijay Chandru, Chairman and Managing Director, Strand Life Sciences, Adjunct Faculty at the Center for Biosystems Science and Engineering at IISc to the program. Professor Chandru will speak to us today on exponential technologies and the perfect storm for digital health.
Thank you, Tiffany. Let me get the screen up. There we go.
Perfect, we can see.
Great, yeah. So, it's certainly a pleasure to be here and an honor to be asked to give the first of these talks today. I came back to campus as an adjunct faculty member after a 12-year sort of break where I was an entrepreneur. And and in 2017, when I was thinking about what course I should teach, I decided to design a new course around digital epidemiology. And that was a bit prescient in the sense that, it certainly prepared me a little bit to what began to unravel this year. And for those of you who haven't seen this new book out in MIT Press by Arup Chakrabarty and Andre Shaw, it's a wonderful read, and it's called Viruses, Pandemics, and Immunity, and I would strongly urge you to take a look. I did call the talk Exponential Laws in Technology and the Perfect Storm for Digital Health. In some ways, my interests in digital health have obviously now taken a little bit of a center stage because of the challenges posed by the whole COVID crisis. But I think this has been obviously something that has been developing for a while. I call these the exponential laws in technology. It's pretty clear. We all have lived and profited from Moore's law. The other sort of exponential law that is very exciting, and what I've spent my entrepreneurial energies on is Flatley's law, which is the law of improved performance in genome sequencing, and of course we're all waiting for the really sort of inexpensive, almost instrument-free, point of care type of sequencing to arrive, and it will. And I think while Moore's law has probably reached the second half of the chessboard, maybe around 2006, 2007, I think in genomics we're just about starting to see the effects of that steep exponential improvements in technology that would happen at the when you reach 2 to the 32 times improvement in technologies. Obviously, uh, you know, a science city like Bangalore, responded to the crisis with science, and and the Indian Institute of Science was, in some sense, an epicenter of that activity. But really, all the scientific institutions of Bangalore participated, and I'll try to mention some of the um, you know neat things that were done. So mine is more of an overview talk than specific technical work that I or my students have done. On the first slide is actually the effect of this whole sequencing technology and how um, a young virologist who's probably one of the bright young stars in Bangalore, Chitra Pattabhiraman, a virologist trained at the National Center for Biological Sciences and now on the faculty in neurovirology at the National Institute of Mental Health and Neurological Sciences, was probably the scientist to really understand clearly what was happening with the virus genome, and was sort of, as the disease progressed, was sequencing the virus and analyzing the data to educate us that there were about 6 different lineages of the virus that had come into Karnataka, and various contact representations of the lineages, the clinical status, and the spatial distribution of the lineages uh, was very neatly analyzed by her. Um, I mean, she actually sequenced only about 50 genomes to begin with, but even that gave a very rich level of detail. And I think most importantly, she made this connection between genomics and epidemiology. And I think this is actually going to be very critical in also, in many such viral pandemics that come up, that we will be able to actually link very clearly how uh, the viral clades, so to speak, will affect the epidemiology and the spread of the infections. She was also a voice of sanity because there were all kinds of headlines about a new strain that had never been seen before, and etc. And I think she kind of sorted many of those things out. Well, one of the effects of having that sequence well understood was that people who were in the diagnostics area were able to jump in and try out many ideas. And so Bangalore, being sort of the tech innovation hub for biotechnology in the country, also showed that it could respond. And here, for example, is a lab in Bangalore called Achira Labs, which very quickly developed 3 different testing technologies. The Obviously the ELISA antibody sero test, and interestingly, it's turning out that neutralizing antibodies seem to be related to IgG, that is receptor binding, and so if you can actually test through these ELISA tests the specific type of binding that that the IgG antibody has, then you can actually use that plasma more effectively. That was one thing. The other was the RT-PCR kits, and the 4-color RT-PCR is actually helpful and gives a little higher sensitivity. And they also have an instrument-free antigen test that should be in the market very soon, and it will be at a price point of a little over $1, somewhere between $1 and $2, and so will be very competitive. I guess Abbott has introduced a test at about $5, but this will be a little bit less expensive and probably will have about the same characteristics. So that's very exciting. There was some very neat work done on compressed sensing and pool testing that came out of IIT Bombay, the mathematicians there, Manoj Gopalkrishnan and Ajit. But I think the actual testing and the validations happened in Bangalore at the National Center for Biological Sciences. It has now been validated at several centers, at the Tata Memorial in Malabar in Mumbai, and at the Harvard Weiss Institute, and is now an entrant in the X Prize competition for being able to achieve price and volume testing efficiencies, right? So this has been an exciting development, and we believe can really be an important game changer going ahead. You at about 2% infection rates, this can get you about a factor 10 improvement, and no sample needs to be retested because this system is invertible, and you can actually measure the CT values through this technique. We had an interesting development on campus. I'm not sure this was already presented. The Go Corona Go contact tracing, which is now actually running on campus. It's also deployed at 2 other campuses in the country, at IIT Jodhpur and IIIT in Hyderabad. And it's being supported now by the NSF equivalent to the Department of Science and Technology in India through a program called Rakshak.
It was presented in June.
Right. I'm sorry?
June symposium, it was presented by Yogesh.
Oh, it was presented. Okay, great. Excellent. And then, you know, there's been just so many different, you know, contributions made, and we call this the WCS, the Electrical Engineering Computer Science Division's COVID Warriors, right? And we had a symposium where, you know, all of them presented, and we're actually now, just today I got the podcasts that have been recorded about all their stories, and we should soon have that up on the Institute website. And we also have a YouTube channel where these podcasts will be broadcast. And so, as you see, you know, some of these may have been presented, some will be talked about today. I think Ganeshan and Deepak Subramani will probably speak today, and of course Rajesh probably spoke in the first meeting, and that work is very you know, very significant work. The one aspect that I did want to mention also about testing was, sorry, I didn't have that slide, but I think Meher, who will be speaking later, has also been responsible for developing some new primers for the COVID testing kits for the RT-PCR. So he has a startup called Veneer, which has develop some of that. So you'll hear from him, of course, on a different context today. So there's been phenomenal response by the IISc faculty, and this is just from the Division of Electrical Engineering. Computer science is obviously work on vaccines, drug discovery, and various other aspects as well. I think just like to end with a couple of pointers to the next thing that we're trying to do now is actually to build a decision support framework that actually puts a lot of these pieces together. And one new piece that we're adding is a sort of a game theoretic framework on top of all the surveillance and contact tracing modeling that is just being put together. I'll just mention it and probably end with this slide to say that this decision framework that is being pulled together, again, as a funded activity of the National Department of Science and Technology, is being headed by Chiru Bhattacharya, who's the chair of the Computer Science Department. Rajesh and I are co-PIs, and Nitin Koshi from the Cisco center at IISc is also a co-PI. So our idea is to actually put all this, the testing, the contact tracing, and the simulation models, the game theoretic protocols together to actually try to build a decision framework for the administrators of campuses around the country as they reopen to help with the safety as we go forward. So this is sort of a more of an integration project that's going to be take a lot of teamwork to pull together. So let me end with that. Thanks again for having me here today.
Thank you so much, Professor Chandru. That was very informative. I think combined with the Go Corona Go session we had in the spring, it really helped us bring a much greater perspective to everything that you're doing. Thank you so much. Now I'd like to invite back to the stage our Dean of the USC School of Engineering since 2005, Dean Yanis Yortsos. He will be presenting on a comprehensive spatial temporal infection model with applications to COVID-19, co-authored with Asad Oberoi and Harisankar Ramaswamy.
Thank you, Tiffany. I think I don't see my, okay, here it is. If you allow me to share the screen, I can then go ahead.
Perfect, you should be able to.
Okay, I don't see.
Green button at the bottom.
Oh, here it is. Thank you. Okay. So I'm sharing.
Perfect.
Do you see that?
We see that it's operating. Perfect, we can see it.
Very good. Okay, well, thank you so much. And thank you, Tiffany. Welcome again to everyone. So this is a work that Asad Oberoi, who is Professor Oberoi, who is also on this call here, and his student Harisankar Ramaswamy. We worked together the last maybe couple of months, maybe a little bit more, on trying to understand actually the epidemic and trying to do this using analogs from chemical reaction processes. Well, you know, I'm a chemical engineer, and anything that I can see, I look at it as a chemical reaction. But actually, what we found here is that by using this type of mindset, you can actually explain a lot of things that somehow either have been missed or perhaps underestimated in previous models. The approach that we follow here is a continuum approach rather than a discrete approach. So it's different than the agent-based modeling or individual trajectories of people that include, let's say, contact tracing. And it looks more as a continuum mechanics problem and try to understand if you were to follow this approach, what kind of policies will be recommended, also how to explain things like contagion waves and the like. So this is a presentation that I would like to condense in 20 minutes if possible. And so I will skip some of the slides. This presentation was made originally for a longer period of time. So please do not feel offended that I do that. I will be more than happy to share the entire presentation or ask questions with others as well. Just like at IISc, at Viterbi, we have a significant effort going on. We call it Viterbi versus pandemics over here. And this is a series on COVID-19. It's a lecture series that started last week, continues, and it's every Thursday at USC. And anyone who wants to participate or take these lectures is more than welcome to attend. Tomorrow, there is a fluid dynamics of the spread of COVID, biology and disinfection for COVID is on September 24, and so on and so forth. Again, we will be more than happy to open this to people from outside USC and be able to, for anyone who's interested in participating. We gave this lecture last week for the first time, and Assad and myself talked about modeling the epidemics as a chemical reaction process. So why is this important? The most important aspect here is that we deal with why does it come as part of a chemical reaction process? It's because the contagion is between human and human. In other words, it requires contact of some sort of proximity. And for this reason, it minimally requires, those of you who are familiar with the SIR model, it requires three components: susceptible individuals, infected individuals, and recovered individuals. The recovered individuals include as well people that have perished, right? What are the important variables? The most important variable is the number of people per unit area. In other words, the spatial distancing. This density has been underestimated or has not been used in previous models. I find this actually to be puzzling because the key to infection is proximity, and proximity is essentially can be characterized by the density of people per unit area, the spatial distancing. And so that's actually a fundamental component in our thinking that this can be approached using a chemical reaction methodology. And we, of course, need to model how the rates these populations convert to another. So we thought that we can look at the problem as a chemical reaction. So here's the two chemical reactions that happen. The first reaction here says that the susceptible people interact with infected to produce two infected people. And that's actually how the contagion works. So we like to understand what is the rate of this reaction here, to go from here to there. These reactions are irreversible. They don't have a reverse rate. And then the infected individual become recover or die. And that also is a irreversible chemical reaction. So if we look at this as two reactions, then we can model this using the mass action, the law of mass action kinetics that tells you if you have two reactants like this, what is the reaction rate to go in this direction? And if you have a reactant like this, what is the reaction rate that goes in that direction? So what is the analogy with chemical reactions? The different subpopulations, let's say S, J, R, can become chemical species. So we think of them as chemical species. Think of oxygen and hydrogen that creates water. Number densities are the equivalent of molecular concentrations. Just like in chemical reactions, the rate of the reaction depends on the concentration, how many molecules exist per unit volume. Likewise, the reaction rate here will depend on the number density, the people per unit area. And the reason we don't have volume is because we live in essentially a two-dimensional world. Infection rates are chemical reaction rates, and this approach can allow you for spatial transport by essentially, oops, something happened here. Let me go back to my, can allow for advective, diffusive, or dispersive fluxes. Now, there are more complex models that include asymptomatic, secondary infections, and so on and so forth. And one can include them in this type of formulation, except that you have to introduce more species. What we try to do here is simply consider the existing 3 minimal species, see what lessons we learn, and then go from there. So this general model allows you to put essentially advection in the model, diffusion, and reaction. So if you like to know how, let's say, the infected species changes with time, then, or the susceptible species change with time, there is a convective part, advective part, which is mobility. There's a diffusion part, which has to do with random movement, and that's actually can be captured by either, let's say, Brownian motion or anything more complex than that, and a reaction rate, which can be captured by the equations that we had before. So there's a lot of technical terminology that's involved here. I don't want to waste your time with all of this, so I will just go fast through some of these parts so that I can give you essentially the fundamental results of the problem. So we define also an overall density. This is the overall density of species per unit area, species meaning the population. Now, why is this important? It's important because we know that urban areas and rural areas have different rates by which the contagion happens. And the way to characterize this difference is really by the spatial density. There are cities where there is extreme density. This happened in New York City. I'm sure it happens in many cities in India as well, where the density of people is high, and therefore, effectively, the contagion rate will be higher based on the kinetics that we'll describe in a moment. And so these are the corresponding reaction rates that you have to put in this equation here. So you notice that, let's say, the reaction rate for, if I use this parameter here as the susceptible species, is a product of 2 concentrations. So the reaction rate here is a nonlinear term, and that makes the equations actually more interesting, and also makes them provide some interesting stuff with respect to the contagion waves that we'll show later on. So these are the infection rates, and that is the recovery or perils rate. So in essence, it's an SIR model, but in terms of areal densities, which is appropriate for such processes. And in terms of, that also gives you something more important than simply providing areal densities, as we'll show in a moment. So let's first of all look at the parameters that exist there. The key parameters are the kinetic rate of recovery or death, which is about 1/14 days. This is a classical time that is used. This is in our equations, of course, is variable, but the typical number for it is for inverse of 14 days. The most important parameter is the reaction rate between infected and susceptible. And that has essentially is this parameter K, this kinetic coefficient K. It depends on the frequency of the collision, and that will depend on density and on the contact. And we expect that K will increase with density of both infected and susceptible. But we also know something more important, that contagion is negligible below a certain density. So you don't expect this to be simply an increasing function of density from 0 to a maximum density. Rather, we expect that there is a threshold. So K will be 0 if the density is below a critical density, let's say corresponding to 6 feet. Maybe you can make it, this is a parameter in our model, so you can make it anything you want. However, fluid mechanical calculations show that in a typical environment, our rho 0 can be actually is a function of the environment, and outdoors rho 0 is actually larger than indoors. I'm sorry, smaller than larger in terms of density than indoors, because of the fact that we have different conditions for the fluid mechanics of the contagion. So an important part of what we do is we essentially have an unusual kinetic parameter, which is 0 below a certain density, and then it's an increasing function of density after this density is exceeded. This is something that has not been included in previous models, which is a strange, as far as I know. We submitted, by the way, this paper for publication, so we'll see if we have missed a part of the literature on that. But in our opinion, that's actually a characteristic discriminant of this particular model. As a result of this, also it's meaningless to be providing area-wide averages, let's say for states or for countries, without making differentiation on density. High density areas are going to have a lot more probability of infection than low density. Conversely, if you recognize that and you have apply very strong behavior in high density areas and you do not do this in low density, you may actually reverse the contagion. And we have a diffusion coefficient for random walk. We don't, I think this is the random walk of people. I'm not sure that I understand. I know the human dynamics for random walks, but that would be a very interesting thing to consider. What is actually the random walks of people in different environments. In this particular case, we calculated for office work. There is a coefficient of diffusion, which is 2 orders of magnitude larger than molecular diffusion in gases, just to show you how the analogy goes. Actually, in some of the calculations that we made, this parameter is a lot more than that in order to match some experimental results. So here are the governing equations. They're all over there. So I'm just going to just jump this. The most important part is this parameter R0. And let me take it over R0. So you can see, if you look at this equation here, these monster equations, there are 3-dimensional parameters. There is a parameter that includes mobility, a parameter that includes the variation of density, and the most important parameter with this parameter R0. So R0 comes out naturally in our model because of the fact that we have dimensionalized everything, and it depends on density and the extent of contagion. So that's an important parameter, and let's go over here to say a few words about that. If you look at the initial rate and you look at this equation here, you can see that the initial rate is this parameter here, is rho R0, with R here is the extent, essentially the recovery, the number of recovered people. So initially it will be 0. So S also is dimensionless, so this is initially equal to 1. So the initial rate is this. So you can understand that because there you have the IDT is proportional to this, this is an exponential rate. So the initial infection will grow exponentially if this is greater than 1, or will decay if this number is less than 1, right? This, of course, is well known that there is an exponential initial rate. However, it comes out naturally in our calculations here as well. R0 depends both on density and the extent of contagion. That's another result that we have found, that R0 does not simply depend on density, but it depends as well on the extent of the contagion for obvious reasons. The more people have been infected and then or they're recovering, the less their probability of infecting others, and this should come as part of the R0 as well. So we have a formula for this, and we can calculate it. So if I look at this formula here, this R0, which is the most important part, contains these parameters here, which essentially depend on environmental factors: facial covering, masks, isolation of infected, increased air circulation, or vaccination. All these are in these parameters here. It increases on density. That depends on behavior. Okay, and behavior meaning that, you know, and that's basically where spatial distancing comes in. It's in this parameter here, because if the density is less than a specific number, then of course this parameter is 0, and then that makes R0 0 or very small, and essentially that explains why one has to follow spatial distancing or wear facial covering because of this parameter here. So if everyone in the world follow this approach in essentially having this parameter R0 become less than 1, then any initial rates will be not exponentially growing, but rather decaying, and essentially the problem will be contained. So to me, a lot of this has to do with the fact that people are either underestimating the importance of this parameter, and, you know, by containing this number here to be less than 1, and you can do this by simply playing with this number here or the density. And this, of course, is part of the important health policies that people have articulated. Then I think the contagion can be contained. So that's an important part of that. So we made a lot of results, a lot of simulations. I will just focus on a couple. We recover the SI-like model. We create infection herd curves. We talk about herd immunity. We also have some results on the initial conditions, which have to do the importance of initial conditions on the, and what effect do they have on the spread of infection. And then we talked about spatially variable interactions and how infection waves develop. I will simply show two slides because I really don't have time, unfortunately, for all of that. This is the classical infection curves, right? So this is here is all fraction of density. So these are the susceptible fractions, starts from 1, initially no infection, the infection starts, and then of course this goes down because more and more people are infected, and then reaches a stable point, well, an equilibrium point at the end of that. This is the number of infected. Think of the red curve here, goes up, goes to a maximum, and then goes down if the infection is over. The green is the rate of the recovered, starts from 0, and then at some point you get to this point here. If you wish, this number here is what we call herd immunity. Herd immunity will be the total number of recovered people, if you wish, what percentage of the total population is, which is the same as 1 minus the total number of susceptible people at the end of the recovery. What people do not understand is that the herd immunity depends on R0. In other words, in order for this curve here to be stable and nothing to happen after that, you have to keep the R0 the same. This is the R0 that allow you to go down here. If your R0 changes by changing behavior, if people think that, well, we're done, everything is gone, everything is stabilized, the infection is gone, and change in behavior, then what's going to happen, a second wave will appear. This happened actually in the States in the summer. And I think this is really the tragedy of this, because people do not understand that in order to keep what is known as herd immunity without a vaccine, for example, you have to make sure that you do not change behavior and keep R0, R0 to be the same. Or to have very effective mechanisms that the moment there is an infection discovered, to keep trace it, quarantine it immediately so that it doesn't grow. So this, so the fact that the herd immunity changes with R0, it's shown here. So herd immunity is, so this is the curve that corresponds to this. So this is low herd immunity at low R0, high herd immunity at I'm sorry, you will have a lot of people that have been infected, if you like, when R0 is high. And this is how the curve looks like. Another important thing to consider, and then I will not belabor more on this particular curve, is the duration of infection. So this is the curve that shows the duration of the infection, the time, based on this one curve here, as a function of R0. You can see that the duration of infection, in fact, is higher at small R0 and then decreases as R0 increases. It's kind of a counterintuitive that the more intensive the infection, the less the shorter period it lasts. But actually it makes sense, because essentially the more intense it is, you have a lot faster propagation of the infection. Everything happens in a faster time. And as a result of that, the infection essentially decays. The time for the duration decreases. The corresponding time here, because we have lambda equal to 14 inverse days, corresponds to about 5 months. So that's essentially what this is. This is approximately about 5 months. So some results from this. Herd immunity is a function of R0. This is something to be understood, and I don't think it's understood. I think the public needs to understand that. And the herd immunity is stable to perturbations, but is not structurally stable. In other words, if you change R0, it is going to not become stable. And that's actually another fundamental problem here. And finally, the duration of epidemic is longer at lower infection rates. This is an example of this, in which you have an infection going, then policy starts, let's say, go from R0.3 to R0.8. So you can see immediately this start decaying. And then at this point, people said, great, we reached herd immunity. let's go back to business as usual. Well, if that moment you go back to 3, then you have this second wave coming in, and therefore your herd immunity, or the people that are susceptible and they're infected, goes from here all the way to here. So again, that explains the effect of relaxing restrictions in the second wave. One more thing, and I have 2 more things, and then I will stop. So what is the effect of initial conditions? So we simulated different initial fractions. So let's say this is starting with 10 to the minus 2 initial conditions of infected people. So essentially the seed is 10 to the minus 2 all the way to 10 to the minus 5, which is this curve. What you see is that the initial conditions have no effect pretty much whatsoever, if they are small, to the shape of the curve. It simply translates the curve from this point to this point. You can prove this, that there is an exponential shift, and essentially the effect of the initial condition, in other words, if you restrict the number of initial conditions of infected people, you essentially buy time to go from here to here. That is the importance of restricting the number of initially infected. This allows people to actually go into a public policy campaign to control R naught and so on and so forth, and say, look, an infection is coming, will be exponentially fast. We have some time to deal with it because of the fact that there is a delay in this from one place to another. As a result, the most important part of initial condition is simply to allow people, to allow a country or a state or a city or an area to take the necessary measures in order to be able to stop the spreading. If people do not do that, then the infection will come up, because as you can see, it doesn't really matter how you start, it will always come back. And this is a result of the exponential growth. The previous speaker talked about exponential growth. I don't believe that the population at large understands what an exponential means. And because of this, people think that, you extrapolate linearly, which is actually the worst thing you can do in a situation in which rates are growing exponentially fast. And all these parts here are growing exponentially fast. Okay, so I will jump here to the effect of diffusion to finish it up. So a lot of things, if we allow for diffusion in the problem, in this case, we take not advection, but simply in diffusion, then what we find is that we're looking for traveling waves. Is there a way by which there is a steady state solution in a traveling wave coordinate? And the answer is yes, you can. And we find this is the velocity. This is all in mathematical terms, and I apologize for all the math here. But you can find there is a wave velocity that essentially transfers the infection from one point to another. And so I'll show you here. I think I have, yeah, here is how the wave spreads. So it starts somewhere at minus infinity, minus 75. Now, so the red curve is the infected people. You can see how the infection spreads this is a one-dimensional problem in the x direction. So you can see this very nice wave that is very similar to the wave the shape that you have when you have a batch problem. So you have this going, keeps going, and then essentially goes with the same shape with the constant velocity. You can see that the velocity here is constant across the domain. It's actually a very nice result to see. I will jump this part here, will jump this part, and say simply the wave velocity increases with the square root of the diffusion coefficient. So if you don't have diffusion, you're not going to have a wave. So that's another thing about containment and lockdown. So if you want to prevent diffusion of a wave from one place to another, or actually the propagation of a wave, what you do is you simply kill the diffusion coefficient, and that's essentially the lockdown that people do. I think the Chinese did this in Wuhan, and other people do to just basically completely stop the propagation of a wave. And you can see it from this simple parameter here, d. The velocity is also increasing with the intensity of the infection. The more intense the infection, the faster that. I will jump this particular thing here, and then I will show you a little kind of a final, my final slide here. Let's assume that you start with 4 quadrants. Northwest has an R0, 2, Northeast 3.5, Southeast about 2, and Southwest 3.5. Now, these are not characteristic of the United States map, so please don't take any offense if you live in the Northeast or the Southwest that I say has great high R0. I just put it here for simulation purposes only. These are statics and show how the infection goes. And let's start it here in this particular. So the infection starts at northeast, keeps moving, very stable, because this is a very stable system. That's the problem with this infection. It's not unstable. Then hits the areas where R0 is small. So it goes slowly there, but then there is the Southwest, which actually fast R0, and there it grows faster than the rest. And this is essentially one way by which this infection moves from one area to another. That's very idealistic because, you know, the system is very simple, but you can do a lot more interesting work and apply it even to a city. You put different correlations for R0 because R0, remember, depends on density, and you can do all kinds of interesting stuff and all this way. So these are my conclusions. Understanding the spreading of epidemics can benefit substantially from reaction diffusion problems. It's very important to include spatial densities because we don't. Kinetics can naturally incorporate this spatial distancing. The R0 variable is a function of both the spatial density and the process extent. We recover easily the SIR-like models. The fact that herd immunity is a function of R0, it is very important to keep in mind that, you know, we can't simply say we conquer the disease if we have not changed and then change R0, unless we change the parameters that control R0. In this particular case, let's say by immunization, in which case then of course R0 can go down to very small numbers. And the effect of initial condition is only relevant in that it buys you time to take policies to reduce R0. And one final thing, the diffusion is necessary to initiate the propagating of infection waves, the mobility part. And we have a way by which we can calculate all that. And the approach applies to additional species and demographics. I'm sorry I took so much of your time. I wanted to condense as much as possible in this presentation, so I would be more than happy to answer questions. Me and Assad would be more than happy to answer questions, and thank you for your attention.
Thank you so much, Dean Yortsos. I know you had to rush through a lot of this, so if you're interested in the extended version of this talk, Dean Yortsos will actually be hosting an exclusive presentation tomorrow at 12 p.m. Pacific Standard Time, in case there are any late night engineers out there and you want to join in, but this will also be recorded. I will add the registration link to the chat. If you're interested in the Viterbi versus pandemic series, please email me at ttay@usc.edu and we will give you special access to the library. I received quite a few requests already, so thank you so much for sending those over. Now I'd like to introduce Professor Ganesan and Professor Subramani from the Department of Computational and Data Sciences of IISc. They will be presenting on spatiotemporal predictive modeling framework for infectious disease spread.
Thank you. I hope I'm audible and also my screen is visible.
Yes, looks perfect.
Oh, thank you. Good. I thank Professor Vijay and as well as all the organizing committee members for giving an opportunity to present and share our experience on the model which we have developed recently. And this talk, I'm going to just give an idea about what are the PDE model that we have developed in the last 6 months. And we call this as a spatiotemporal model. The reason is we are including this both spatial and as well as the inertial internal coordinates. That's the brief outline of my talk. And before going to that, of course, it's already introduced. This is a joint work with my colleague, Deepak Subramani from my department. And yeah, so now I'll go to the talk. That's a brief outline of my talk. First, I will spend a few minutes on the mathematical modeling of infectious disease. And then I will spend some time on the PDE model that we have proposed for the pandemic or any infectious disease. And then if time permits, I will spend maybe 1 or 2 slides on how this high dimensional PDE is solved because it needs some special technique to handle the curse of dimensionality associated with this high dimensional PDE. And then maybe I will share a few screen results and maybe the pictures, how the projections and some predictions that we have made and how it was proven right, all these things. And I will conclude my talk with that brief summary. To start with, again, of course, to this audience, this part is clear, right? So the part which I want to highlight is about the infections or the severity of the infection. Most people, roughly around 85% experience only the mild to moderate respiratory illness, and they might recover even without any treatment. And the remaining might get more severely infected or even can lead to death. And the main point or the question is, since we do not have a vaccine or at least the proven treatments, that's why the pandemic or the COVID is becoming a big issue. So these are the points that have drawn our attention. And then, of course, we want to say that okay, we are not an epidemiologist, right? So we are again the computational scientist and the FEM guy working on CFD mainly, but because of a lot of interest and we have put some effort, we started like a hobby work, and then eventually we ended up with some kind of a model. And I hope the proposed model will be useful in even for other predictions as well. So these are the basic definitions. What we are in almost, or we are in the pandemic. That means it's epidemic with the passport. It's no country and it's not local. It's a widespread across the nations. So we are in the pandemic situation. What is epidemiology? We started looking into it after we started work on the COVID. So it's mainly about analyzing the data and then study and the distribution, especially the data in the sense of who, when, where, and the patterns, and determine health and disease conditions. And also we can roughly, or we can informally, you can say that epidemiology is a collection of statistical tools. But of course, we need causal inference and as well as the required rigorous mathematical modeling, and also especially the fitting the or not. I will come in a minute. And also we need, especially when you keep on increasing the dimension coming from the system of ODEs, when you move on to the PDEs, of course, the previous talk is a nice introduction to the PDE models. Then obviously the computational sciences, computational solutions comes into the picture. Just to give a brief idea, what about the mathematical models, especially in terms of these predictive models, what we have, I will take a different example rather than the COVID. I will go into the finance sector. In the finance sector, what we have is like a lot of stock markets, and we know the stocks and the histories over a period. And using this data, what we are trying to do is try to fit some parameters and write it all these dynamics in terms of equations. And then after fitting these parameters in the dynamical equations, and we try to solve these equations and try to get the projections. And if you are capable of projecting it correctly, then of course one can invest and then become a billionaire or millionaire and so on. So that's a rough overview. And this is exactly what we are also doing with any infectious disease modeling. We have the data, and from this data, what the idea is, we have to describe these dynamics in terms of mathematical equations, and after describing it, fit the parameters using the previous data and solve these equations, and then run it for the future time, and you will be getting the updated values or the projections. And this is about the mathematical modeling of the infectious disease. So when we looked at these models, especially for the infectious disease, and we can classify these existing models into 4 categories or 3 categories, and another category is just added. The one of the most commonly used, and of course the popular models are the compartment models. And the compartment models set up ODEs, where SAR and all these models comes into the picture. And the next model is agent-based model, and the third is stochastic models. And now what we are seeing, especially after this COVID, a lot of, at least a couple of PDE-based model. The previous talk is also PDE-based model, and ours is also PDE-based model. So when you compare to the compartment models, it's about only the numbers which you are predicting and so on. When you compare to the agent-based, it's about modeling the individual and the tracking the individual agent. Agent is nothing but the infected people. And stochastic model, you are bringing the probabilistic laws and so on. So in our approach, we are a bit different, especially when you talk about the PDE model. I will come in a minute why and how it is different from the previous presentation. We will be seeing it. Just before going to that, just to set the notations and everything correct, right? When you talk about the compartment models, one of the popular models, and of course we can find many presentations on the results based on the SIR, susceptible, infectious, and the recovered case. The idea is how these values are changing over a period of time. So that's defined as a coupled system of ODEs, and then the most key parameter is R naught. The people talk about even the news and social media. People talk about the R naught. R naught is of course the how the infection is getting propagated, or whether it's growing or whether it's under control. Everything depends on the R naught. So if, R naught is the one which gives the right predictions, especially for this system of equations. And of course, from the SIR, we can see several variants. SEIR, instead of taking the entire population as an susceptible, we can also have a susceptible and exposed, and the exposed are the one who are vulnerable for the infections, and so on. So keep on building the SIR models and so on. And the reason why I took this picture from the news or the media is this is one of the first projections using the SIR model, and this is also Oxford model. This is what presented somewhere in the March. You can see that the SIR model, what we have predicted is somewhere growing some till the end of March, and immediately the March 23rd, India has announced the lockdown, and after the lockdown, immediately the COVID cases came down, and also the authors have proposed the periodic lockdowns kind of thing, 21 days, 28 days. And of course, we can see that why this model, whether we are able to predict it correctly or not. And of course, it is not the case now in India. That's now the total cases of 5 million infected cases as of today. So that's we have missed that. And then when we looked at all these information, SIR models, the system of ODEs, and the questions which came to our mind is whether the information just producing only the number, how many are going to get infected, how many are going to get recovered, and how many deaths are going to happen, whether having only this information about the numbers or these information are enough for planning lockdown unlock strategies and for planning public health policies such as quarantine rule, hospital beds, because we know from the very first slide that all patients or infected people need not have to admitted, and need not go to hospitals as well, symptomatic, asymptomatic, all these cases comes. Just a number may not have this information. And also more importantly, even when the vaccine comes, whether having only the numbers, will it be enough for the vaccine, and even for the treatment schedules, will it be enough? And also we thought, how about if we have a more insightful predictions to formulate science-informed policies, just instead of having the numbers, how about in order to have more information? When you talk about the more information, what we are talking about is it's not only about the number, but the number with the distribution in terms of the location, the numbers with the distribution of severity of infection, the number with the distribution of infection, duration of the infection, and also the population age. So it's not only about the number, but with more detailed information. So what I'm talking about is just to go, before going to the model, what I'm just to give an pre-look. It's not only about the 2,000 active cases, but instead of having just a one number, instead of that, if we have the information about how many of them are in which group, for example, the patient age, from 0 to 100, and also instead of having just only the number about the 2,000 active cases, how about we have the information about who are all having the severe, who are all having the mild infection, who are all having the asymptomatic, and all this information. That's where the other direction, the y direction curve comes, the COVID intensity. So when the intensity is 0, of course, they don't have any infection. When the intensity is high, maybe 1 in the scaled version, they are severely infected. And also infection age is more important in our study. The reason is, for example, the incubation period of 5 to 6 days, and then the recovery of 14 to 15 days. So these information, if we have, instead of just having the number, if we know that how many of them got infected on which day, and what's the age of the population, just not only the number of infected cases, we thought if we have these insightful predictions, that might be very helpful for science-informed policies for making this type of information. So that's the ideas comes into the mind. Then immediately the question comes, how to model it. Then again, of course, this is how the spatial also, that's where the idea comes. It's not only about the information with the numbers, but also information across the nation and across the space. That's what the spatial information comes. Then immediately the question comes, okay, how to bring in all these. Of course, the idea is very nice and it's better to have all this information. The question is how to bring in all this information into a mathematical model. Again, I have to go back and agree that, okay, all this idea comes from the chemical engineering. So basically the model which we are taken or which were derived is the idea basically comes from the chemical engineering, process engineering, where the population balance modeling idea comes. So just to set the notations clear and also to understand the PDE that you have proposed it better. Of course, T infinite is the time which we want to do the computations till what time we want to do. And omega L, these are the, we call it as an internal domain. Then the internal domain, we consider the three key parameter, and LV is the infection severity, and LD is the duration of infection, and LA is the age interval or age of the population. So this is what I have talked about. When LV equal to 0, then that means the population or the people are disease free, and the LV equal to 1, they have the maximum severity. Definitely they need the treatments. And we can also set the threshold for LV. So for instance, if their value is less than VSIM, then we can call it as asymptomatic, and the value is more than VSIM, that are symptomatic. And based on this, we can also have the predictions, okay, who are all having a very severe infection, and how many of them are really need the beds or ventilators, oxygen, all these things can be obtained, at least predicted from this model instead of just the number. Okay, so just the one or two slides about the equations. Of course, this is the PDE based model and including the internal domains. The I is the infectious density, and I want to make it clear that I is not the number, it is a number density. That means I is a function of time, space, and the internal parameters. It's nothing but the number density function of the infected population. And the first part, especially the dou I by dou t plus the divergence of ui, is what we have seen in the previous presentation about the spatial or the PDE model, which you have seen before. That is about the spatial representation. The third and the fourth term, and of course the fourth term is also the infectious death and the recovery. And the third term is the key, which contains the internal coordinates, where I have talked about how the infection is going to affect and so on. Okay, all other parameters I do not want to spend much time here. The key parameter here is the C. C is the recovery rate and the infectious death rate. And just to get the number, how we can relate it to the SIR model, how is it connecting to the previous model? Sorry?
Mission about 5 minutes. We are running out of time.
Sure, I will complete in 5 minutes. Yeah, so what we have seen before is the I is nothing but the number density function, and if you integrate it over the entire domain, then what we are going to get is the total number of recovery cases. And if I integrate I over omega, then I will get the total infected cases. That is nothing but the I in the SIR model. This is how we get the numbers, and of course the question comes how then new infection is getting spreaded, and how the new patients are added into the infected population. Of course, it's a bit complicated model, but what I want to stress is, so you can ignore if you want the more detail, you can go to our archive paper and then you can have a look. But what is more important is the R0. R0 is the infection rate, which we have seen before. So the one difference compared to the SIR model, and here is the R0 is just not entering as a number, but it entering as a distribution. That's how the B nuke is coming into the picture of one. And in this B nuke, we have also included the quarantine. Gamma Q is the quarantine. Even though people have got infected, but if they go into the quarantine, then definitely they are not going to infect the susceptible population. So all these things are incorporated into the model. That's where the 1 minus gamma Q comes into the picture. Of course, all the other parameters need to be fitted. And if you look at the infection where B nucleation, it includes the social distancing, SD, interactive index, also the hygiene index, and also we can also bring in the comorbidity variables, like if they have the pre-disease and other things. That's how the age of the population comes into the picture. Okay, so I will skip about the model and other things just to give the idea about how we calculated the initial number when we start the simulation. So what we do is, just I want to make it clear that when you start the simulation, of course, we can fit the data with the available in the literature or available from the government source. But that's not actually the infected population. The infected population is the one which are available on that day, which are known on that day. In addition to that, whatever the newly infected, including the people those who are in the incubation period, so it will take like 10 to at least 5-6 days. So we have to consider all those population as an infected population when on day 0 of the simulation. So we have taken this also into consideration, and we have fitted and we have started with the right initial condition I0. And after starting this initial condition, of course, how to solve this equation and other things I can skip. If you are interested, you can go into the literature how we are doing it, because this is a 6-dimensional PDE, including the time. So we have this 2-dimensional space, time, and then we have taken the 3 internal coordinates. That's why the 6-dimensional PDE comes. Of course, when you want to solve the high-dimensional PDE, you will end up with the curse of dimensionality, and you need a special technique, and this special technique is an operator splitting finite elements technique. I will skip these slides how the operator splitting is interested, but if you're interested, you can also visit the web page and other thing. Okay, so this couple of slides about the numbers which you have predicted. This is how after integrating the infected population and integral over the entire omega, then you will end up with, you can also retrieve the number of infected cases, number of active cases, disease, recovered, all these numbers. This is equivalent to SIR model. But if you zoom into this number, I will move on quickly. If you zoom into the numbers, then you can get even more detail. It's not only about the number what we have seen in the previous curve, but you can also get the information of how many people are really infected, 50% and more, or the severely infected or less infected, asymptomatic, and which group of people are severely infected. For example, in this case, between the red zone is about between the maybe the 25 to 45 is the red zone, and also in severity infection is in the middle. And if you can look at the population infection age, it's in the days. So you can also see that it is less than 50 days. That's clear. So any COVID comes, it's around 20-25 days. This is what we can see. Then it's a dynamic case. We run over a period. That's how we made the projection. Just the last slide before the summary. This is what we have predicted. Of course, we have done the fitted the parameters data over a period of time, and this data we have fitted on August 6th. On August 6th, we have predicted that India will have the COVID case of 40 lakhs by first week of September or 1st of September. This is what exactly we got. We see the numbers, and today it's about 50 lakhs. That means we are having that around 5 million cases, and by first week of September, 4 million. That's what we have seen. And also we have performed the different scenario analysis, and we can go into the numbers. We can check when is going to get the peak and other information. That's the last slide. So what we have seen a PDE-based model for infectious disease. Of course, it's not just a spatial of dimension. We have also included the internal coordinates about the 3 internal coordinates. That's why the high dimensional PDE comes into the picture. I did not talk about how to solve this high dimensional, but if you're interested, you can go into you can check our manuscript. And what we have projected is bang on so far till September, and in fact till December we have also made some projections, and we have performed different scenario analysis and also the other cases. And currently, we are also including the serological survey taking into consideration, especially the infected and the antibody cases and so on. So with this, once again, thank you very much for listening my talk, and I hope I'm convinced that, okay, the new proposed model will be having a more insight into the pandemic and useful to other diseases as well. Thank you.
Thank you, Professor Ganesan. And our apologies for having to keep this short. So please know that this session is being recorded and will be sent out to all participants within the next 48 hours. Thank you so much again. Now I'd like to introduce Bhaskar Krishnamachari, our Professor of Electrical and Computer Engineering at USC Viterbi. He will give us an update on digital contact tracing and risk estimation for COVID-19. Please welcome Bhaskar Krishnamachari.
Thank you, Tiffany. It's my pleasure to present before all of you. So I'll be talking about two pieces of work we've been doing in the context of COVID-19. The first has to do with a model for estimating risk for populations. And the other has to do with some updates on location estimates using mobile contact logging systems. So in this first work, I want to talk about a new risk scoring metric that we developed in collaboration with folks at the city of LA, as well as researchers here at USC Viterbi. That is a scoring metric, which is using a time-varying SIR model, which was talked about earlier in this workshop. And the goal here is to have a risk metric that is directly proportional to an individual's probability of getting infected within a certain community. So we see here on the map different communities within the County of Los Angeles and color-coded by risk levels that would help an individual understand, if you're in this community right now, this is how risky it is for you to go out and participate sort of in the community, and you can take potentially measures corresponding to your local assessment of risk. The key idea of this approach is to start with the SIR model that's been talked about before with some uncertainty quantification as well, and use it to predict the R sub t. This is like the R0 that has been mentioned. It's the effective reproductive number, but we're treating it as a time varying parameter. And once you have the sort of time varying measure of the increase in infections, if you will, then you can use that to estimate the probability of infection within a community. Essentially, this would be proportional both to this R sub t parameter, but also the current number of infectious cases within that community. And of course, inversely proportional to the number of people in that community as well. So this sort of new measure of risk, we believe, is helpful because it's intuitively telling you as an individual, what is your likelihood of getting infected in the near future within your community. We've built some software that draws daily data from the County of Los Angeles, parses it, runs it through this SIR modeling, estimates the R sub t, and then ultimately generates the risk estimates for each community within LA County using this. And this pipeline is open sourced and available on GitHub for others to build on and perhaps adapt to their local communities. So I want to share with you some of our results from running this pipeline on data from LA County. Here we see the data from LA County just smoothed, showing the number of daily new cases over time. And you can see that we've definitely seen it rising all the way through midsummer. And since then, due to some newer measures that were put in place, the cases have been falling, although again, at the very end of this, where we are today, there's a little bit of a concerning, maybe a plateau, or hopefully it's not an uptick again that's happening. Here's a visualization of the daily R sub t for the entire LA County. And you can see that when we run this kind of new case data through the pipeline to estimate using an SIR model, we get a pretty clear picture of times during this year that the infection cases have been growing dramatically and times when they've been more stable or decreasing. And so, as you know, the ideal situation would be for this R sub t parameter to be at or below 1, ideally below 1. And you can see that at different times, particularly early in the year, there was that first wave. And then when the first safer at home restrictions were applied, there was a decrease in this R sub t. But in kind of the late April, early May timeframe, there were a series of outbreaks that happened in LA County, particularly in certain populations like prisons, as well as the meatpacking industry, which was allowed to open. And then sort of all through the year, there was a steady kind of relatively high value of this RT above 1 for much of June and July. But then after kind of July 4th, there was a sense in the community for a lot of people that it was time to relax, and that resulted in a huge increase actually of cases in midsummer, resulting in newer strict measures that were kind of reasserted by the county. And we can see that, for much of August and where we are now through mid-September, it's been quite good. On the other hand, now in early September, we had Labor Day, and it appears we're seeing an increase again after that. And so sort of looking at RT helps us understand some of these patterns over time. This is just the same type of analysis, but applied to communities within Los Angeles. You can see that there are particular and different variations in sub-communities, as was alluded to earlier, as a function of their different densities, different movement patterns of citizens within that community, different types of businesses that they have, and so on. And we can see that there's quite a bit of variation across different communities within LA County. This shows the risk metric that we have, and essentially it's a measure out of 10,000 of a probability of getting infected in a certain community. Right now, this is for the entire LA County. We can take the same type of analysis and apply it on a per community basis, and we see that as of yesterday, there are particular communities in LA County, particularly in what's called the Valley, San Fernando Valley, and parts of East LA that are at higher risk than others. And we're continuing to kind of track this on a granular basis in our work. The other work that I want to mention has to do with contact logging using Bluetooth. I'd mentioned in our last workshop some work that had to do with privacy-sensitive contact logging and exposure notification, some of which has informed the efforts by Google and Apple in their exposure notification system via Bluetooth. More recently, we've been asking the question, can you use these Bluetooth signals between mobile devices to estimate distances between mobile nodes? And can you improve the estimates if you're allowed to use distance estimates from a network of devices that are near each other? And so mathematically, this is a problem of estimating distances between pairs of devices given a matrix of measured radio signal strengths. And in some cases, these measurements may not be available. And so you have kind of a matrix with some missing elements of radio signal strengths, and the goal is to try and estimate distances between them. Now, typically and traditionally, you could use a signal strength versus distance model, use empirical measurements to fit that data. But recent work has shown that this is actually quite complicated in real environments with mobile devices because of the effects of things like what happens to the signal strength when you keep the device in your pocket, or what happens if it's in a purse. And the measurements from a recent study have shown that the signal strength can be significantly affected by the placement of the device, for example, in pockets or purses. So in this work, we've taken a number of algorithms for network distance estimation, ranging from very simple direct estimation techniques that use the signal strength and models to generate these estimates, to more sophisticated schemes that use ideas from multidimensional scaling and semi-definite programming, and Spring models that are iterative in trying to calculate these distances that best fit the radio signal strength data and models that we have at our hands. We're looking at these different algorithms, both under ideal conditions, but also under more typical real world conditions. And there were a number of scenarios for which data has been collected in the study prior to ours that looks at, what are the measurements typically like for groups of people sitting at a table or riding on a train, for example, or standing in line outside a grocery store. And in comparing these different algorithms to both somewhat more ideal types of settings as well as more realistic settings, what we find is that although in kind of an ideal radio propagation environment, one might prefer very simple signal strength estimation schemes that just do pairwise distance estimates, when you have dropped signals, when you have pockets and purses, multiple device models, and varied types of indoor environments, then it's better to look at more sophisticated iterative techniques as well as semi-definite programming applied to this to improve both the error performance and find the right trade-off between true positives and false positives. One thing we found is that the performance of these schemes with real data is not actually as good as one would like. In particular, if you're trying to estimate whether the distance between devices is within 2 meters or not, which is helpful for COVID to keep safe physical distance, that the true positive rate for the most sophisticated algorithms is not higher than like 63%. And at the same time, it has a pretty high false positive rate of above 40%. And so even the best state-of-the-art algorithms don't seem to do quite so well when you take into account non-idealities like putting your devices inside pockets and purses and so on. And so there's clearly more work to be done in this direction. So with that, I think I will actually close and summarize. We've been working on new approaches to assess risks from kind of an individual perspective on a per community basis. The models we've developed are available as open source software, and I would encourage anyone interested to adapt it to their local community to take a look at our work. And with respect to Bluetooth contact distance estimation, we see that you need more sophisticated algorithms to estimate whether in trying to automate the estimation of whether individuals are near each other or not. But clearly more work also needs to be done in that direction. With that, I'll stop. Thank you.
Thank you so much, Bhaskar. Living in East LA and seeing your model that it is higher risk, I will be especially careful. Thank you so much for displaying that. Now I'd like to introduce Cyrus Shahabi. Dr. Shahabi is the professor of computer science, electrical engineering, and spatial sciences, and the chair of the computer science department at USC Viterbi. He is here today to present on PrEP, Pandemic Risk Evaluation Platform, Beyond Contact Tracing for COVID-19. Please welcome Cyrus Shahabi.
Thank you. So you guys can see my slides?
Yes.
Okay. All right, so I think I actually gonna follow pretty much what Bhaskar was talking about, and maybe going a little bit into the details of contact tracing. So before I start actually explaining contact tracing, just a couple of terminologies. So these are from the papers that I put the references below, especially the second one. This actually came out April 1st, 2020 online, and then later in May it was published, and it used real data from Wuhan to calculate some of these numbers from real world data, including things like the incubation period of the COVID-19 disease or the coronavirus, as well as this what is called the generation time, which is basically a time between the infection of the source and the infection of the target, the recipient. And in case of COVID-19, first of all, as you can see, the incubation period is actually a little bit lower than the generation time. So higher than the generation time. And what that means is that potentially a person can be infected and maybe even pre-symptomatic and transmit the disease. And that's the real challenge, as everybody knows, with COVID-19. So contact tracing traditionally is based on folks basically interviewing a confirmed case. And usually when you look for a confirmed case, this is somebody who is symptomatic, right? So otherwise you don't know that the person might not even get tested. So you don't know this person is actually infected. And then once they interview this person, they identify all the contacts that this person had in the past, and they try to alert those contacts and basically say, you what? Yes.
We're not seeing your slides.
Oh, you're not seeing the slides?
We were, and then it disappeared.
Oh, I saw at some point I got this on Spotlight, and I think that removed my slides from sharing.
Perfect.
Okay, sorry about that. Move on. So, yeah. So basically, So I was here basically, so I define incubation period, generation period, and then the fact that you can transmit disease when you're pre-symptomatic, and then contact tracing basically is this top idea of interviewing confirmed cases, usually symptomatic cases. And in case of COVID-19, it varies. Basically, you might go 5 to 10 days or sometimes 14 days in the past to basically identify all the contacts and inform them to either ask them to get tested or potentially quarantine them. The pluses of this traditional approach is that you can identify transmissions over what they call fomites or through environment. You can also potentially identify indirect transmissions like that A infected B and B infected C. So you might even go as far back as even informing C, the indirect transmission. The challenges though is that when you talk to people, they usually don't remember from memory all the people that they met or the places that they went. So that's one challenge. Another challenge is that if you have, usually these contact tracing are used at the beginning of the pandemic, so there are not that many cases. However, if this is going to happen while the pandemic is going on, which is the case now, you need to scale it up, and therefore you need a lot of people to operate as a human contact tracer and talk to all these folks, and that might take actually a lot of time. And then most importantly is the latency, which is basically from the time that you identify the person who is asymptomatic and then try to contact their contacts in the past 5-10 days, that might be already too late, and the contacts have already been in the population and talking to other folks, so that the latency is very important. So as a kind of a solution to these challenges, this paper actually introduced this concept of digital contact tracing, which was basically using mobile phones. And they did a study based on the mobile phone data and some of the data that they had from the COVID-19, and they look at this value of R0, basically the productivity rate that was mentioned in previous talks, and they showed that given the fact that you can only talk to the symptomatic folks because you don't know about the pre-symptomatic cases, if you can do that only for a small percentage of the people, and that you kind of successfully isolate, because again, half of those going to be pre-symptomatic, so you cannot even contact trace them. Still, you can get to this green area, which is basically the reproductivity rate is low, which basically stops the spread if you have almost zero delay in isolation and quarantining. Basically means that this is instantaneous contact tracing, and this is only possible if you do this in a digital contact tracing form. So that was the paper basically made the case for digital contact tracing. And after that, there are a lot of efforts. Bhaskar mentioned actually the efforts of Google and Apple, which is and the technique that he actually also pioneered, which was using Bluetooth. And the idea there was that if you have two people who are close to each other enough to potentially transmit the disease, they're also close to each other. Their phones are also close to each other to transmit some sort of a token. And once you exchange these tokens, if later on you know that one of them is infected, basically you can go and look at all the tokens on this person, the infected person's phone, and realize that, oh, at some point in the past 14 days or 10 days or 5 days, this person was in contact with this other person because the token was there, and therefore you can immediately inform the person. So that was the idea for the Bluetooth approach, basically. There are some limitations to the Bluetooth approach. So first of all, it cannot detect transmission over environments like surfaces and so on. It cannot detect indirect transmissions, basically, and that's sometimes it's important. I have some graphics here for the indirect transmission. Because of the, again, asymptomatic cases, you might potentially have a lot of high false positives, because basically there are a lot of people who are basically close to each other, but not, their phones are close to each other enough for the Bluetooth to pass tokens, but not close enough to actually pass the infection. And then mainly the approach is very much an alert-based approach, where you keep a kind of notifying folks about being in contact. And this has the potential, that especially with high false positive, this has the problem that potentially people can become numb to it. And at some point, basically, you get too many false alarms, and you basically might turn off your notification. So, and then finally, and this is, I think, is the most important problem here, is that because of the privacy issues, because they want this to be fully private, all these data about the tokens and so on are stored in a decentralized manner. There is no information about where the contact happened, the location, and so on, and therefore there is no centralized data collection. And this is the main problem of not being able to use the data for any sort of policy decisions or spread models, the various spread models that was discussed today. Most of these can improve if you have real data about the contacts that this technique actually does not provide. So what we were kind of proposing is to go beyond that. So we are basically saying that we need some sort of a community app, for example, for a neighborhood or for a campus. And it's an opt-in app, it's voluntarily, but we want to collect more data. And by more data here, we mean not only just the fact that two people will close each other, but the locations, the traces, the duration, some of the things that Bhaskar mentioned, for example, if we can actually find the exact distance and so on, this would be a very nice data set that we can utilize. And then we can put all these together and come up with some sort of a risk score, which is basically based on how many infected cases a person was in contact with, for how long, and then how many potentially infected locations this person passed through, and use all that information potentially in the machine learning type approach, and calculate the risk score between 0 and 1 for the person and show it to the person. And this can have a lot of advantages. For example, if you see that your risk score is high, you might go get tested. If you see that the risk score of a location is high at a certain time, you may decide to skip the location and go to some other, for example, grocery store and so on. So, and then there are some other advantages that I can talk about it actually through this schematic. So basically the idea here, what we're proposing here is that going just beyond just the contact tracing, but has create a whole framework for pandemic risk evaluation. It starts from the app to collect location and co-location data. This can go to some sort of a spatial temporal analysis module that can take other auxiliary data sets and report this to some sort of a dashboard for health practitioners that they can actually do the contact tracing and confirm cases. So we still have the human in the loop, unlike the Google Apple approach. However, once these practitioners identify the confirmed cases, then you can use these new data set plus the location data to do your risk analysis and inform the spread analysis models. Some of the models that you already heard can be informed using not only the location co-location data, but also potentially the results of risk analysis. All of these can go into a single dashboard that can be utilized by a policymaker to basically come up potentially with intervention. So for example, say, hey, anybody with risk score above such might stay home and so on, where these intervention again can be analyzed and see how it improves the total spread. And of course, risk analysis, the output of the risk score can also go back to the app, so the user himself or herself also know about his own risk score. So we started working on this. We got some rapid funding from NSF with some of colleagues at Emory and UT Health to build the contact tracing backend to basically utilize these trajectories of people moving around to identify various types of transmissions, including fomites transmission and indirect transmission. We also are working under the same project to calculate these risk scores based on various aspects of contact, the duration, the location, the risk of the location, and so on. Even looking at some analytics to identify people who are potentially friends with each other based on their previous contacts over time. And then, as you know, there's a higher chance of transmission if two people actually know each other or have been in contact before. So taking all those into consideration. On the spread analysis, we actually collected or got access to a very high resolution check-in data that for the entire United States during the pandemic. So we're looking at that data set, and the idea is basically mimic an infection. We don't have a real infection data, we just have the co-location and the check-in data, but we can mimic an infection, and then given the co-location and the duration and so on, we can run a simulator and using various models and basically see how many other people got infected. And then based on our risk analysis model, using this data, we can calculate the risks and then basically do interventions. And then once we do the interventions, for example, if somebody's risk is 0.8, they should stop movement, we can inform the model again and look back and basically see whether the intervention was successful. These are some of the mock-ups of the dashboards that I mentioned. This is for health practitioners to see to identify cases quickly of for contact tracing. There's a policymaker dashboard that can identify hotspots. Actually, we built a version of this. Maybe I can quickly show a demo utilizing aggregate data at USC. This was based on Wi-Fi access points, where we can identify how many people are at certain buildings at a given time. So this shows basically the USC campus map. There are two campuses, UPC and Health Science Campus. So I'll go to the Health Science Campus here, and you see each building basically identified. The color supposedly shows the number of people at that day, at that time in that building. So as you move over different days or hours of the day, the color changes, which basically shows that more people showing up as the day goes by. And then you can actually select a specific building. And then when you click on the building, you can actually see the various floor plans of the building. As you see, these circles are basically the locations of the access points. And then the radius of the circle shows how many people are connected to that access point. We give you a sense of density of people in that location. This does require some aggregation from various data sets that we're working with, and potentially you can build some heat maps to show basically more graphically how this is spread. So imagine you have this for the density, and if you have confirmed case information and you can superimpose it on top, it will be very revealing of basically what's the status of the spread. Of course, there are a lot of security privacy considerations. We're aware of those. Here are some of the things that any contact tracing app or pandemic framework should abide to. It should basically based on voluntarily and consent. It should be transparent, minimizing the information collected, and of course the data should be destroyed after the hopefully the outbreak is over. There are some immediate privacy enhancement that you can do, and we're working on those as well. So for example, these location traces can be stored locally. So there is no reason actually to store this in a centralized location. You can also give the utility to the user to basically change the frequency of the location check-ins that are stored, the precisions, for example, at the zip code area level versus at the lat-long level, or retract certain locations that the user want to keep private. So these would give some privacy control to the user. You can also have this iterative privacy approach where the user at the beginning might basically share very coarse location and time temporal information. But as you provide incentive to the user by basically saying that if you share this location data, the more accurate you can save like 5 or 10 people's lives. So in that scenario, the user might actually in an iterative process provide more precise locations. There are several research opportunities here that some of which we're working on right now. And I have this one last slide, which is basically more kind of rigorous privacy work can be done as well by using various techniques like searchable encryption, adding noise to data, and doing the whole analysis in a privacy preserving manner. And these are supported by various sponsors, each one of these projects that we're working on. All right, I think I'm done.
Perfect. Thank you so much, Professor Shahabi.
Thank you.
Now I'd like to introduce to the stage Rajesh Sundaresan. Professor Sundaresan is currently associated with the Department of Electrical Communication Engineering, the Robert Bosch Center for Cyber Physical Systems, and the Center for Networked Intelligence at IISc. He will be presenting today on Swabs to Labs tool and the Zero survey designs.
Thank you. I hope you can hear what I'm saying.
Yes, we can hear you.
Are you able to see my screen?
Yes.
Okay. Okay. So I'll speak about the Swaps to Labs tool that we have developed. Okay, so let me wait for this to go away. Yeah. I had an initial ambitious plan of also speaking about Zero survey designs, but I thought the better of it. I will say a few words about it at the end. So a few words of acknowledgement. This work was supported by the Center for Network Intelligence, which is a Cisco CSR initiative, and the Indian Statistical Institute, Bangalore. So here's the core team that developed this: Nidin, Sharad, Sarath, and Nihesh. I would particularly like to call out their names, and Shivatreya. And we've also been working with the Karnataka IT team and the Karnataka Health Department. So how did this begin? About 2 months back, I spoke about the agent-based simulator that we had built, a fairly sophisticated simulator which simulated the 12.3 million individuals in Bangalore with various activities, households, offices, schools, marketplaces, trains, and so on. And we also had a sophisticated modeling of the interventions that are there. So these were the various phases of lockdown, and then there was a recent lockdown in Bangalore. And these were the predictions that we had, the yellow curve for a particular scenario with that 1 week lockdown. And you can see that there seems to be a reasonably good match with what we are seeing in Bangalore. So we took this to the health department. They looked at us kindly and said that thank you very much, but we actually need something else from you. And that's how the Swaps to Labs came about. So here's the background. So Karnataka is a state in India. This is the location. It's a southern state with about 67 million population. We have about 30 districts. These are the 30 districts. About 1/6 live in this Bangalore area. The remaining population is spread across various pockets of Karnataka. So Bangalore is going to be handled separately in the problem that I will describe today. So we'll ignore Bangalore and we'll focus on the rest of Karnataka. So the health department said that we have been ramping up testing quite a bit. So these are the number of tests. This is from the Karnataka Health Department bulletin from yesterday. So over 1 million antigen tests and over 2.5 million RT-PCR tests thus far. So yesterday alone, they conducted 37,000 tests and 31,000 of the RT-PCR and other tests. These are in situ tests, whereas the RT-PCR tests involve collection of swabs and moving them to a particular lab, which is PCR enabled. And overall, that's about 68,000 tests, which is about 1/16 of the number of tests that are carried out in India. There are roughly about 30 states in India, but a significant number of testing is actually in a few states, and Karnataka is one of them. So what's happening is there is quite a bit of collection of these samples, and these all need to be moved to places where they can be tested. So quite a bit of transport involved. How do we optimally do this? So here are the kinds of issues that we are seeing. So this is the kind of cases that Karnataka is getting. So in the various districts. So these are positive cases. And you can assume that the number of actual samples collected are roughly between 3 and 10 times the number of cases. In Bangalore, it's about 3 times the number of cases, but in some other places, it's about 10 times the number of cases. So quite a few cases are being, quite a few swabs are being collected, and they need to be moved to various places. So here is a snapshot of how efficiently the testing capacity is being used. So here I have listed the set of labs in the Bangalore area, but they are representative of the problem that Karnataka is facing. You will see here the daily capacity of each of these testing centers. So 36 for Apollo Hospital, 300 for the Indian Institute of Science. So we actually have a local testing facility which is used by the state, and the capacity is about 300 tests a day. And then you'll see several others here. So all of these are the capacities that have been indicated to the state. But if you look at the number of tests done in the last 3 days, or the average per day, and view it as a percentage. So the Apollo hospitals in Bangalore has been used only 50%, has been operated at 50% capacity. IISc at 25% roughly. The Institute of Stem Cell Science at 65%. But you will see some others have been overloaded. There's the Bangalore Medical College at 161%. NIMHANS, the National Institute of Mental Health and Neurosciences, at about 300%. And here's something, the Kidwai Memorial Institute of Oncology at about 1,300%. So over 12 times they are operating at over 12 times the capacity. St. John's is another one that's also quite overloaded. Here is another one. Eurofins Clinical Genetics is a marked lab for several other entities, and they are at about 700%. So clearly, or surely, we can do better. And what I'm going to describe is a very simple and elementary solution. And let's see what it is. So the key players in the current allocation procedure are the following. So there is a district surveillance office for each of the 30 districts. There's an officer or the staff at this place that's involved in entering how many samples have been collected. So each of these districts actually has several, it has a district hospital and about half a dozen or so community health centers or sub-district hospitals. Now, samples are collected from all of these places and they come to the district surveillance office, and from there they are distributed to various labs. So here, that's this information. Swabs are collected by various health workers and brought to the DSOs. Now, they must be distributed to about 113 labs, and these labs are RT-PCR enabled. Some of them, a few of them, have repurposed some of the tuberculosis testing mechanisms. And so they are cartridge-based nucleic acid amplification test entities. And there is also an indigenous version of this, which is called TrueNat. And some of these labs can run this as well. Roughly, there are about 4 testing labs per district. They have varying capacities. Some are closed for maintenance or for routine quality checks, or some may be closed because there might have been a contamination. So there's quite a bit of varying capacities as well. So here are the capacities of a few labs. So you will see these numbers. I earlier displayed the capacities of the labs in Bangalore. These are the capacities of labs across the state in the various districts. Some of them are in Bangalore, but some across various other districts as well. There are a total of 113 of them. So the current procedure is as follows. The district surveillance office or some staff from that office enters the number of swabs that have been collected for the day. And this must be done before 7 p.m. Then a drop-down menu is provided, and in the drop-down menu, there are several primary labs that have been mapped to this particular district and one secondary lab. And these are shown with their available capacities. Usually these available capacities are based on yesterday's information, the backlog, and some processing information that has been collected over the day. Often that information comes in a somewhat delayed form. But nevertheless, that's displayed so that the district surveillance officer can take this into account. Then the DSO makes a request to send some samples to some target labs. Now, this is asynchronous in the sense that each of the 30 districts will do it at different times. And the request to send mechanism is to ensure that labs are not overloaded or they have the option to say no. So there's a negotiation, there's an acceptance or a rejection. And if there is a rejection, there's a reassignment as well. So the primary labs that have been mapped usually accept, but the secondary labs can say no because some other They might be primary labs for some other district, or some other another district may have sent swabs to that particular lab, and they might have accepted it. So subsequently, the next morning, labs, they do the test overnight, and the labs enter the tested numbers on the following day. This is expected to be done by about 10:30 a.m. Often they do not enter because there are too many portals where they have to enter. Each result has to be manually entered in a particular portal, which is the national portal. And then the results are communicated to various authorities, and then eventually distributed to the health authorities and the patient. But then because that's more important, a lot of attention is given to that, and often they don't enter how many they have serviced in this particular portal. The other thing that I told is a variable is perhaps the capacity for the next day is only one half, perhaps because of contamination, maintenance, somebody's on leave, and so on. So all these things lead to inefficiencies. So here are some problems. The DSO's attention, the district surveillance officer's attention, is taken away from core health issues to transport issues. There's also unnecessary negotiation and quite a bit of human intervention in the allocation. And information is not effectively collected and used, which is resulting in wasted capacity or wasted cost, and also test delays. And I don't have to overemphasize the importance of timely testing and passing on the information to the patient as quickly as possible in a disease like COVID. Also, it's quite clear that this kind of negotiation-based thing is not scalable. So we need a better solution. So what were the requirements? The State Department gave us this information. So the DSO staff should be able to enter the sample numbers as and when they arrive. So for example, they might come from each of the sub-district hospitals or the what are called the taluk hospitals. And as and when a particular set of swabs arrive, he should be able to enter it and get it allocated. This might happen multiple times. There are about half a dozen of them associated with this district. Also, these asynchronous updates can happen up to a cutoff time. And the cutoff time you can take to be about 7 p.m. or so. The allocation should be automatic. Otherwise, the DSO has to apply his mind and make decisions. And we would like to have him focus on more important issues, or have the DSO focus on more important issues. After the cutoff time, we would like to bring a centralized and automatic matching of the leftover swabs and capacities. But during this initial phase, we would like to do the allocation in a local and optimized fashion. Subsequently, we would like to enable the DSO that has not been able to enter it in a timely manner, but an automatic allocation has already happened, to still go ahead and allocate and use the leftover capacity. The other things to take into account are that there are variable lab costs. Some labs have 36 wells in their RT-PCR machine. Some others have 32. Some others have 96. And they might have multiple machines, etc. So there is economies of scale in some case and not so in some others. So there is variable cost per lab. So one would like to optimize it. One would also like to optimize the travel times to each of these destinations, because that's additional cost. Also, if the number of samples is quite small, which is to be transported to, let's say, a far off place over 300 kilometers or so, then if there are just 50 or so samples, then perhaps you can just do an extra run on the RT-PCR machine, and you might be able to save on cost. And the local lab may be willing to do this. So try to see if this can be done. These were the things that were sort of given to us by the health department. Now, here is a schematic for the allocation. So there's data that the DSO will enter. There's data that the various labs will enter, which will involve computation of the backlogs, maybe today's capacity, if there is closure of some labs and so on. Also, the new labs may be added at a somewhat slower scale. And that input is also something that could be taken into account. Maybe new areas like Bangalore urban may also join this particular allocation procedure, and that could be included here. With all these inputs, the allocation engine should run and then put out the allocations, as I said, in an asynchronous fashion, and then once in a synchronized fashion, and then perhaps a visualization engine. So here's how the algorithm goes. So these are the 30 districts of Karnataka. First, we do a local, so the first thing that happens is there is an update, which is the familiar linear recursion for those that are familiar with queuing theory, which kind of tells what's the backlog or the number in queue at each lab. Then we update the capacity based on this. So these things need to be processed today on a priority basis, so the capacity is reduced. The capacity could possibly be negative, in which case we take the capacity to be 0. In round 1, we look at an allocation within district. So here is what is known as the Bangalore Rural District. This district is what is called the Chitradurga district, and this district is called the Davangere district. So each of these districts, in fact, all the 30 districts in round 1, will do a local allocation. And the way we do this is we sort of introduce a leftover bin for accumulating all those which we have not been able to allocate within this, and assign a reasonably high cost to it, so that things will get accumulated there if they have not been able, if you have not been able to assign it to labs here. Then we do an allocation within districts via an LP. I say an LP, but it's actually fairly straightforward. You just have to go in the decreasing order of cost, which is the cost of operation plus the cost of transport, and then do an allocation. So this is fairly straightforward. For distance, we actually use travel times instead of distance, based on the suggestion from the health department. And then what we do is we assign these swabs to those labs and then reduce the capacity. So if there are some leftover swabs that need to be assigned, perhaps to other places, we see if it is at most 96. If it is, then we just overload one of the labs locally. And this happens at each one of the 30 districts and can be handled in an asynchronous fashion, district by district. And this happens until 7 p.m. or so. And then comes the synchronous part, which is round 2. So for this round 2, what we do is we take each of the districts once again. This time I'll focus on this district called the Belgaum district. What we do is we look at if an allocation is to be done for the district, that means that there are some additional samples there which need to go out of the district. And what we do is we look at a 3-hour distance around it. And we do this for every one of the every one of the districts as well. And then do a centralized LP optimized allocation, but within the 3-hour window. And when we do this, once again, we do an allocation and we check at each of the labs, each of the districts, whether the leftover is at most 96. If it is, we overload the local lab at this stage instead of at this stage. If it is more than 96, then we do the same thing, but this time for all of Karnataka. And it's a repetition of the same as round 2A, but without the 3-hour time constraint. So here are some assurances that can be given for this particular algorithm. So there's a transport out of the district only if the district capacity is exceeded. There's a transport beyond 3 hours only if the local capacity is exceeded. And so this kind of solution is something that we have developed. There is also a sort of rendering of this, a visual rendering of this, where there is a color coding which says what's the load in each of these districts. And then this is the source map. And there might be some transfers, and this is the destination map. So we accumulate all the loads that are likely to come to these districts in the labs that are located in these districts. And there is a map of this as well. So for example, you can see that there is a somewhat less load. Okay, let's look at this. So Bangalore Rural has a high load, but not enough labs. So the load from Bangalore Rural has gone to some other places. If you actually move the mouse over there in the actual application, you will be able to see the number as well. Additionally, there is a map like this, which sort of says where the samples from Udupi, for example, are going. Because there is additional testing capacity in Bangalore, there's quite a bit of transfer into Bangalore from all these places. This is the solution of the LP. So the current status is that we have sort of integrated it into a test platform, and we are waiting to integrate it into the state's portal. The goal was to finish this yesterday, but we have been delayed because of some additional changes. Hopefully in a day or two, this should be integrated and should be live. Next steps, we would like to include Bangalore Rural, which has not been included. Roughly, you would have seen quite a few cases in Bangalore. About 3,000 cases come in Bangalore every day at this time. So we would like to include this also and have a good allocation there. The other thing that we want to do is we don't want to bring swabs to the district surveillance office. We want to be able to take them directly from the place where they are collected to the testing center. That's actually fairly straightforward to do. We just have to introduce each of those as a smaller DSO entity in our system, and it will automatically do the allocation. The next thing that we want to do is predict and move kits ahead of time, particularly the rapid antigen test kits, because we know that the sensitivity of the rapid antigen test kits are quite poor because they are highly specific. When you know that it's positive, you know that that individual is virus active. And therefore, we could give care immediately to that particular individual. And we would like to move this to places where there is greater need for this. And so some sort of prediction engine that predicts where there are cases likely to arise. And then moving kits ahead of time is something that we are looking at. In fact, we had a solution already, but we removed it because we wanted, in the first phase of the implementation, this out of the picture, and then we will bring it in at a later time. Also, there are some attached additional allocations, like for example, when the rapid antigen test kit's outcome is negative, because of its poor sensitivity, we have to follow it up with an RT-PCR test. So that means that there are attached test capacities that need to be taken into account. And that's something that we have already implemented. We have a test implementation, but it's not something that we'll take to state until we have tested it locally. Then another thing that was requested, but I think it's less of an issue here, is load balancing, and that's also fairly straightforward to add. In fact, it's already added, but we have deactivated it at this moment. So that's all I had on the swaps to labs. I wanted to speak about the Karnataka Sero survey, which is taking place right now. In fact, the whole of last week was spent on this survey. The goal of the survey is to estimate the disease burden in Karnataka, so active diseases, and also estimate the number of people with antibodies to the SARS-CoV-2 virus. So it's something that it's an initiative of the Karnataka Health Department. It's led by an eminent epidemiologist and the state's epidemiologists. Just very briefly, there are 3 rounds, and it's going to be statewide, all 30 districts. 1 round is over, and the data is coming in. The swabs have been sent to various places. The Sera samples have been sent to various places, and eventually they'll be entered into the portal, and then we'll be ready for an analysis. What has happened is that we have leveraged the existing state health infrastructure. So there is quite a bit of infrastructure that has been put in place for AIDS prevention and control, and also tuberculosis surveillance. And there are counseling and testing centers associated with these 2 entities, and they are the ones that have enabled us to do this survey. There are about, in the first round, about 16,000 samples. Each sample takes about half an hour or so. So you can sense that that's about 8,000 man hours. So the entire state machinery was mobilized to get this testing going. And the 8,000 man hours is an underestimation. So as far as the sampling is concerned, the sampling is sort of clustered, centered around these various district and sub-district hospitals for certain kinds of participants. But then we also want to go to the congregational and market areas. So there is some systematic sampling that has been planned there and has been conducted as well. And then there is some additional systematic sampling from a vulnerable list that was prepared early in April, and the list of individuals with non-communicable diseases. So the State Department maintains this list. So we have leveraged this, this particular list. So as for why this sampling, how did we implement this, what's the progress and the results, you'll have to wait for the 3rd Faculty Research Symposium, IISc Faculty Research Symposium. So these are some photographs taken at 2 district hospitals. This one is at Hiriyur, Chitradurga. This gentleman is a District AIDS Prevention Control Unit counselor. His name is Mr. Ashok, and this is the lab technician, Mr. Naveed. And this is me trying to recruit one of the participants at a town called Chelakere, where IISc has a 2nd campus. So I made it a point to visit this particular place. And the corresponding counselor in that center is Ms. Nandajyoti. So thanks very much.
Thank you so much, Professor Sundaresan. The RT kits are a very exciting next step. We are so glad you can join us today. Now I'd like to welcome our final presenter of the symposium, Meher Prakash. Professor Prakash is an assistant professor at the JNC for Advanced Scientific Research. He will be presenting today on different stages, different modeling strategies, adaptive strategies for early stage, detailed SAIR modeling for the intermediate stage, space-time analytics for a mature stage. Please welcome Meher Prakash.
Hello, thank you very much. It's been a pleasure listening to all these lectures, and thank you very much for the opportunity to speak. Let me just begin so that I don't keep people from waiting. Do you see my screen?
We do.
Okay, good. Good 10 o'clock to everyone, whether it's morning or evening. So this is a very brief talk. I'd like to see how I can structure it. It summarizes briefly some of the works that we have been doing, a few works that we have been doing since March of this year. I belong to JNC, as Tiffany has introduced, and in collaboration with IISc and IIT Bombay, we have been doing some of these works. And so these are the 4 questions that we asked over a period of time. Firstly, in March, we were asking where to begin. I'll briefly begin explaining what are all these problems. But in May, when the time came where some of the data began collecting, we started asking, how do we do predictions? And in August, when some of the cities started finishing the first phase of infections, we started asking what just happened. How do we summarize the results that happened so far? And in September, we started asking a new question, which is, can we do some planning based on the evidences that have been gathered so far? This is another question. In some sense, there is an evolution of thought process as more and more data got collected. But at the same time, it's also given that cyclic nature of this infection that maybe there is going to be a second outbreak, or maybe if there is going to be a mutation and a combination which leads to a second outbreak, all of these exercises again have to begin in the same cyclical order. That's the reason I still think these are all relevant. So firstly, to begin, this is a question that we asked in March. Where do we begin? The reason we asked this question is some of these, everybody started hearing about COVID by then. And by then, New York already started having some of the terrible conditions that the hospitals were full and so on. And then the questions began whether India is also going to end up in a similar phase. If yes, or is it that the high temperatures that India has, or the general immunity that the Indians have to several other diseases are going to protect?
Oh, Professor, I'm so sorry. Can you move the camera down a little bit so we can see you?
Okay, I didn't realize you were seeing.
Perfect. Okay, thank you so
good.
much.
Yeah, so we were asking whether the high temperatures are going to be having somehow a protective effect, or the general immunity is going to have some kind of a protective effect, because everything was so new. Nobody knew whether the scenarios that developed in some of the developing countries would still be the same for India. And then immediately after the first level of questions started, the next question was, can we, if let's say the scenario is going to go in the same direction, are we prepared for the critical care requirements? If yes, what do we do about it? How do we predict that? Then the subsequent question was, but do we have enough reports of infection? Because the testing was, of course, limited at that time. In fact, the number of infections were limited at that time. So how do we deal with these uncertainties in the infections and deaths and yet make meaningful predictions was the first challenge that we had in the early stages of the pandemic in India. So the solution that we dealt with was, we just said, many of the eminent speakers have introduced compartment models, susceptible, infected, and recovered kind of models. But we realized that in the early stages, many of these other compartments have very little relevance, because it's just that the infections are going to be on a rise. What if some patients begin to recover? Not a problem, because as far as critical care needs are required, we had to make predictions months in advance so that these equipment can be prepared. And so we had to work with the uncertainties in the data. And it was very important that even if it seemed that we were only making approximations with based on purely the infections and without considering recoveries, we were very sure that that will only put our estimates of the critical requirements on the higher side, which is actually going to be that the country will be better prepared. In that sense, the model looked like it was perfect to deal with the simplest model. And so what we did was that the simplest equation, which is di by dt, is proportional to the rate at which infections are growing. That's what you see. But we discretized it because it did not seem like it was any meaningful to do a continuous predictions in the early phases. And but what we did was something innovative. What we did was we said, okay, the data in one country is probably not enough, but let's see how much we can gain by looking at other countries. So that's where we try to draw upon the universalities in the patterns by looking at other countries. And not only that, we also asked a question, but what if the infections were underreported for whatever reason, because the testing facilities were limited or whatever? Can death act as a surrogate for the infections itself? So by doing these, by doing these and focusing only on the infections, first we could recover the universal patterns in the rise of infections. This is the number of daily infections that you see in record in any given country. And this is, of course, the cumulative infections that have been noted in that country up to that time. And as you can see, all of them fall in a similar lines. This suggests a kind of a universal behavior. And similarly, all the same universality could be seen also for the deaths. So it was coming from physics background, seeing universalities, especially at a time when the data was limited, looked like the way to go forward, because we could exploit the data from other countries to also model what's going on in India. And similarly, we also asked a question, is death going to be a surrogate for infections? Is there a kind of a relation between them? Of course, even now, people talk about recovery rates and how the number of deaths are a fraction, anywhere from 10% to 1% of the infections and so on. So in the early phases, when we looked at deaths versus infections, we could see some kind of a universal pattern, again, coming from different countries. But I'll not go into the technical details, but there was a multiplicative correction factors that was required, that is the beta that you see, and that could be obtained as a given the fit or best fit to the data. And once that could be obtained, we could use the reported deaths as one way to predict the new infections. Similarly, we could also use the reported infections to make the predictions for the new infections. So which means we had two estimates. As anyone who does experiments or computational simulations knows, if there are two independent ways of doing the experiments, it's better, because it essentially sets the bounds for these limits. As I said, we were doing these calculations with a week resolution. These are the different weeks starting from 25th of February. This is data from Italy. And what we were doing was, as you can see, the top of this graph is where we were using the data from the first week and making predictions using exploiting the universality that I mentioned for the deaths that are about to come in the following weeks. Of course, this is the prediction looking from here going into 3 weeks later. But subsequently, as more data got accumulated, we started updating the data, which is essentially a retraining, and we could essentially follow the trend even better. So we had a very good accuracy for a few weeks, and but at the same time, by doing this piecewise approximation and a very simple linear way of extrapolating, what we could do was we could adaptively correct our model every week, and that gave us a way to essentially make good predictions a few weeks in advance. This is again similar thing, but this is the prediction of infections that we have, and red and blue lines are essentially the bounds that I was talking about. One made using prediction, one is the prediction using the data from infections, and the other is the predictions made from reported deaths. The summary is that by switching to a simple model in the early phases where the data was limited, and as you can see here, I'm noting that there is a phase-based approach that we used because that essentially helped us to deal with the uncertainties of parameter estimation in the nicest way. And using that by extracting the parameters from the data, exploiting the universalities, we could make predictions, which were very easily corrected as the weeks went by. So it was as accurate as any other prediction could be, but in the simplest possible way. And based on that, we could also make critical care predictions for different states for the weeks that were following, depending upon wherever we were. These were the ventilator predictions, mainly predicted using the data of the deaths. So that was the first question. Like I said, where everything was new, we were not even sure the Indian data would follow the trends of the data from other countries. And we could establish that it was following roughly similar trends, especially in the initial phases, pre-lockdown and so on. And we could make estimates for the critical care requirements. The next question was, as more data started pouring in, we asked, can we actually make a prediction of how things will evolve, the so-called peak that everyone has been worried about. So as a process, in that process, what we started, this is the work that we finished in that process. And what we did was we resorted to a compartment model, but with one condition, that we started taking into account some of the realistic data, which is, if you see this data that was from he et al. This is, of course, Cyrus was mentioning some of these serial interval generation time and so on. So by collecting these data, by interviews, performing interviews of some people, what this team could do was that they could show that the pre-symptomatic infection was about 44% or something like that. And this is completely different from even the SARS. The blue curve that you see is the peak of contagiousness, and in the SARS of 2003, this peak came 6 days after a person was showing symptoms, which means very likely they were in a hospital setting at that point. So as a result, this COVID presents a very unique scenario that the pre-symptomatic or asymptomatics have been transmitting a lot of infections. And not only that, we also made another accurate calculation. These predictions by he et al. Were only done with 70 people. So by going up to, by basing the calculation on about 1,200 people, we could actually show that the pre-symptomatic infections were about 68%. Pre-symptomatic or asymptomatic infections. So which underscores the importance that we had to work not with the SIR model as was good enough for the previous epidemics, including SARS or influenza, but we had to work with a model which is known as the SAIR model, where asymptomatic or pre-symptomatic, for various reasons, we had coupled them. And we were working with a model in which the infected, the susceptible persons move through these different compartments, where some of the asymptomatic or pre-symptomatic people start converting into infected or start showing symptoms at a later stage, but there is also a parallel path where they start recovering without ever showing any symptoms. So some of this methodology, of course, is public now in the archive we have uploaded. And so as we did that, so this is the mathematical model that we built to address that. So there were three unique aspects of this entire calculation that we did. The first is that we were using asymptomatic fraction in the calculation. The second is that we were using, just like I told earlier, we were using the phase space approach that we developed in this physical review article that I mentioned, and we were using it to actually extract the parameters from the data that epidemiological data that is available. By the time like I said, this was in May, and there was enough data available from different countries, and we could demonstrate the efficacy of this model, as well as the ability to extract these parameters using the approach that we had taken. And subsequently, we could use this model to do many calculations where we could show that This is SAIR fractions as the time was progressing, where we could show that what you see is the IC is essentially the cumulative numbers, but here is the summary that you see, where if there had never been a lockdown, the symptomatic fractions would reach a herd immunity when about 4 to 6% of the population was infected, whereas if you also include the asymptomatic fractions, you would have about 50 to 56%. These were the estimates that we got based on the realistic data and the parameter extraction that we were doing, and so on. So we could address both the asymptomatic fraction estimation as well as make estimates for the herd immunity using the approach that we used. So what just happened is a question that we asked after that. This is again a work where we are talking about trickle down effect, where the pandemic spread from metros to smaller cities. I'll just highlight so what we did is after we created this SAIR model, very recently what we did is we had developed a website based on this model that we were using, and where we could actually get the parameters, the driving parameters, whether it's the rate of recovery, rate of death, whatever it is, all of them for, and of course, parameters like R naught for 200 different districts across India. The reason I say 200 is because that it was limited by the amount of data that was available. Other districts so far did not have enough data resolution to support good calculations. So when we made this website and we made predictions for about 200 different districts, what happened was that we started, of course, these are like the predictions using our model, SAIR model. And we ended up extracting a lot of different parameters. This is the state, this is the district, number of active infections, different parameters, reproduction ratio on a very regular basis. So after getting sheets and sheets of Excel data, we asked the question, but how do we summarize this? So this is a work we did as we tried to zoom into the data, and we did a work of analytics. These are these 200 districts that I'm talking about. They come from about 22 districts, 22 different states, which are roughly arranged north, south, east, west in the right order, roughly from India. And the different circles I'm going to fill right now. And these are based on the innermost circle is the one that is affected by a lot of imported cases, which is probably where cases started because they're metro cities with connectivity to international cities. And these are the cities with the domestic, second tier cities with domestic airport connectivity. And these are the cities with the next level of connectivity with trains. And there is the outer ring, which will come in a second, which does not have much of any of these connectivities. As we started creating these are, like I said, as I go in any one state, as I start going out radially, essentially, I'm reaching out to further and further to the distal parts of these distal regions of these different states. So the first graph, this is from these graphs that I'm going to show very briefly. These are updated on a fortnightly basis every 15 days, starting from May 15th. And the initial highlights, these are the number of active infections. The initial infections were high in Delhi, Mumbai here, and Chennai, which is Tamil Nadu, which are the biggest metro cities in India. And as days went by from May 15th, every 15 days, as you can see, slowly there is a progression going outwards. The number of active infections are shifting outer and outer, which means that, as Rajesh was saying earlier, slowly the remotest parts of the city, remotest parts of the state, they are receiving more and more active infections. Slowly it's reducing, the intensity is reducing at the major cities, metro cities, and slowly it's building up in the smaller cities, which are actually probably not so well equipped in terms of testing or care and so on. But despite this bad news, there is also a lot of good news. The good news is that firstly, the reproduction number, if I see it in March, from May till August, the reproduction number, which was initially roughly around 4 for some cities, these are for the 200 cities that I'm talking about, with an index where the population is decreasing as I go along this axis from 1 to 200. And overall, the reproduction numbers for most of these cities have dropped by the time August has come. So, and of course, so the reproduction numbers are improving. And this is not just in the metropolitan cities where probably there is more awareness, but also in smaller towns. So that's a positive news that there is in general an improving trend. I'll not show the data, but the same is happening with death rates and so on. But this is another way to look at the same graph going from May till August. As you see, whatever the cities with the largest population indicated by the biggest circles, slowly they had high values of reproduction rates, but slowly they start going down as it starts crossing the line 1 here, and many of them are below the line of 1, and just a few of them are beginning to still stay above the reproduction rate of 1. So the death rate also is improving both in cities and smaller towns. That's a summary. And we could analyze to see, is it really the per capita infections that drove this so-called herd immunity or crossing over the peak in some cities like Mumbai or something? It actually turns out that no clear pattern could be identified as it, but at least the data we collected allowed some kind of a opportunity to do this kind of analysis. The last one, I'll take exactly 1 minute, is an evidence-based planning that we have developed. And this is based on the data from United States, where we have recorded the data from the different government policies, how the governors have given different press releases about what fraction of the restaurants could be allowed to open, what fraction of the bars could be allowed to open, what are the activities that are allowed, and so on. But that was all poetic, that was all stuck somewhere in prose, and we converted all those effects into numbers. So what we were trying to do is, how do we connect the government policies so that we can estimate the transmission rates or R0? And like I said, this is the first evidence-based planning which started revealing many interesting things. By working from data from March till August, what we could do was, like I said, we could quantify the effects of policies. We converted all the policies announced by the governors into variables, and we could also make predictions. We could also make calculations for the rates of transmissions of the infections. And to connect how the policies affected the rate of infections, what we did is we used a machine learning model, which actually learned about how the rates of infections. What you see, these two curves, one of them is actually the predicted infection rates as the week number went by, and the other is the actual observed infection rate as the weeks went by. And the results were turned out to be very good for all the states. But here is the most interesting part of the whole data. So far, people still ask the question, how do I know my mask works? How do I know? There is no proof, because it's only in the laboratory conditions that people demonstrate, or otherwise they resort to the human level feeling that, look, don't you see that some Asian countries which have adopted the mask policy have actually shown an improvement? So by using this, we could actually, and one of the very recent developments in AI called the interpretable AI, what we could do was, depending upon how the degree of opening of the restaurant, or depending upon the degree of restriction of imposition of the mask, we could show that, especially in this case, we could show that as the mask was enforced more and more, the contributions to the rate significantly decreased, and so is the contributions with the bar and so on. As more bars were opened, one could see how the effects were clearly the R0 or the transmission rates were increasing. So it allowed us not just to do that. For example, this is a case from Alabama from week number 28 and week number 29. And you could see that...
Can wrap up soon?
30 seconds. In this state, what you can see that in week number 28 to week number 29, as Alabama enforced a mask policy, went from mask equal to 0 here to mask is equal to 2. It had an effect of a protecting effect where it's a blue color, and it from the actually dangerous effect of adding more transmission rate, and because of which actually it went over a peak in the week of 29. It also asked us, this interpretable machine learning model also allowed us to ask many different questions. Is climate having any effect? Or the famous statements by some of the governments which say that you are seeing more tests only because you see more infections only because we are doing more tests. We could answer all of these exactly by using the policies data from the real world, from different US states. And we could demonstrate that it's actually the climatization, which is essentially the use of air conditioner rather than the outside air, which has a very significant effect. And also, for example, this is from an engineering sense, this is the last question that we asked, which is, are any of the policies over-designed? It's like having a table with 10 legs. Do you really need them? For the effect that you are having, can you remove some of the constraints? And I'll not go into the details, but essentially some of the states like California, which if you relax some conditions, do not move too much to the right, means that they are actually, some of the policies are over-designed. So by using this policy, by combining the policy data with the effects that were observed, what we could do was build the first evidence-based model for making planning, which is a step completely different from saying that, let's imagine R0 is the half, let's imagine that I reduce the R0 by 1/4 or whatever. We can actually say, here, pick a policy, I'll tell you what the R0 is going to be. It's actually, we believe that this is the next frontier in terms of making plans, or at least making estimates of what is R0 rather than assuming R0s. So thank you very much. I hope I could convey some of the work that we were doing.
Thank you so much, Professor Prakash. That was amazing, amazing data. And with that, that concludes our symposium for today. To be respectful of time, please send any questions directly to the presenters. And for those of you still with us in India, thank you for staying up with us for this long. For those of us in Los Angeles, have a wonderful rest of your morning ahead. Today's event was recorded and the link will be available and sent out to all registrants within the next 48 hours. Thank you again for joining us. And like we say here at USC, fight on.
Thank you to all the presenters. Thank you very much.
Thanks to all the presenters and for everybody for tuning in.